And this set of rules, whoops, you will notice, if you would be so kind as to look at your ion Bible, down towards the bottom, there is a little box which contains a very condensed version of these, 8 rules. They're in your book. You will be doing oxidation numbers on your test. You'll be doing them on your quiz tomorrow. When you're doing these on tests and quizzes, you'll have the ion Bible with you, so you'll have that little condensed set of rules, and that pretty much covers it. Okay, with a few things that you have to kind of memorize on your own. So, first thing to know is that, did I mention this yesterday? I think I did. Do oxidation numbers refer to a real distribution of electrons? Do they refer to a real exchange of electrons between two atoms? No. Guess what? They're made up. They're made up numbers. Well, not everything is made up. A lot of it is arbitrary names that we give to things that are real. In this case, nope, they're just flat out made up. So we use oxidation numbers for some types of formula writing, and we use them for making some predictions about how things will behave, but they don't correspond to some physical reality. Okay, so I want you to understand that first. What they do is they attempt to kind of describe when you've got two things bonded together, where you're going to find more of the electrons. So they're kind of like a fake charge. They're not an ionic charge. Do not confuse them with an ionic charge. But they're like a made-up pretend ionic charge. That's the best thing I can relate them to. Not a big fan of them, but they have their uses. So, because they relate to how electrons are being shared between two things, if you've got a lump of pure carbon, is it sharing any electrons with anything else? Guess what its oxidation number is? 0. Pure elements always have an oxidation number of 0. That's your very first rule. I don't even know if I put that in the... oh, okay. I was going to say, because that one you really just have to know. If I have a chunk of pure oxygen, guess what its oxidation number is? Zip, 0, zilch, nada, nothing. So that's a big one, because I will, of course, try to trick you, because I'm mean. Now, number 2. When we're approaching doing these, it's one of those things where we sort of strategize it a little bit. We look at what we're assigning oxidation number to, and we kind of run through our rules and see which ones apply. If it doesn't apply, if number 1 does not apply, then we look at number 2, and we start off with the more electronegative element. That's always going to be the one that's second. Okay? That's the one that, if we were trading electrons, would take the electrons. And we give it the oxidation number that's equal to the charge it would have if it could take an electron. So think about chlorine, for example. If chlorine was going to form an ion, what would its charge be? -1. It's going to pick up 1 electron. It's going to have a 1 minus charge. So if we have chlorine bound up covalently, guess what its oxidation number is? -1. It's not really a charge, but we give it the same oxidation number as the charge it would have. The less electronegative element will typically get the charge it's got as a cation if those two don't work together. So if you attempt to use that rule and, hey, it doesn't work, then you have to move on to the next rule. There are 2 elements that have specific rules that relate to them, oxygen and fluorine. Okay? So if it doesn't apply, rule 1 doesn't apply. We tried rule 2, and that didn't work either. We move on to rule 3 and 4. Does it have fluorine or oxygen in it? If so, then we go ahead and assign them oxidation numbers and do a little fancy footwork algebra. We're going to do all this together in a minute. Hydrogen is the, well, actually 3, okay, so 3, 4, and 5. Hydrogen is the other element that's got a specific rule all to itself. This is like, the laws that get named after children who've had tragedies. The oxygen rule, the fluorine rule, and the oxygen's rule, fluorine's rule, hydrogen's rule. So something in the first 5 is going to give you numbers. Somewhere you're going to get some numbers. Then you come down to this algebraic sum. When you're making an ionic compound, all the charges have to balance out, right? Yeah. When you're doing oxidation numbers, all the oxidation numbers have to balance out. If the compound's neutral, they have to add up to 0. If it's a charged polyatomic ion that we're talking about, they have to equal the charge on the ion. Okay? And that's pretty much it. So let's do some practice.